Now we're going to learn about the MOSFET. First, we have to know about the MOS structure. MOS structure is the three consists of three layers. First is the metal, second is oxide, and third is semiconductor. So we can first is the metal, oxide, and semiconductor. And the MOS structure looks like metal, oxide, semiconductor. The metal is work work like gate, and oxide is like insulator, and semiconductor is substrate. So if we get the voltage in metal, we write this VG, and if we if we looks like this structure likes looks like capacitance. So we call this MOS cap. That's why we called this MOS structure MOS cap. This is the basically principle about the MOS. And now I'm gonna tell you about the simply how to draw the MOS cap band diagram. Okay, look at this slide. This level is vacuum energy level, and uh, before talk about the band diagram, we have to know about this. Sorry. Okay. We can use the gate, metal, or highly doped polysilicon, because the highly doped polysilicon work like metal, so we can use metal or polysilicon in to do this. And insulator is SiO2. This day there's another oxide, but we have to know about this, how to SiO2 work like in MOS. And semiconductor is there's two type, maybe P type and N type. Okay. And next now I will tell you how to draw the band diagram about MOS. Okay, here is the vacuum energy level. And as you can see, these two level, this is the highly doped n-type polysilicon, and here is p-type silicon. As you can see in here, the Fermi level in n-type and the Fermi level in p-type is not constantly, so this is not thermal equilibrium situation. This is the unbiased situation, so we we have to know this MOS is not equilibrium. And we can divide this. Here is the metal, oxide, and semiconductor. And difference between this conduction level and this conduction level, this point and this point, and this offset, the 3.1 electron volt, must maintained when we bias or thermal equilibrium situation, and the ionization energy between vacuum energy level and conduction level, and also here, and these two gap are so maintained. This is very important things. So and also the between this XiO2 balance band and between the p-type balance band, this offset also maintained. So let's drawing the thermal equilibrium situation most band diagram. Okay, we can draw first. We will use the polysilicon. So the polysilicon, okay, and the oxide diagram like this. Mm, because we have to we have to this offset, so we have to we made the slope in here and here because the conduction band of the p-type drawing like this in this, and the Fermi level of the p-type on here like this. The Fermi level in n-type draw like this because the polysilicon is heavily doped, so we have to draw sim like the closer the on conduction band. And also we can draw the intrinsic Fermi level about the p-type like this, and we can write this is the make this electron volts like this on here, and 4 4.8 electron volts or so. So and we can draw the vacuum energy level like this. We have to draw slope like here and like this. Okay. Oh, sorry. As you can see, if we draw the most band diagram in thermal equilibrium situation, simply we can draw like this. Uh, Before the next stage, I already mentioned this is not the thermal equilibrium, so we can call this the flat band condition. Maybe I will talk next week about the flat band energy and accumulation and depletion about the most today. But now I'm gonna tell you about the simply just if the band diagram looks like this scaly, so we can notice this is the flat band condition. And we use the polysilicon in here. Now I'm gonna tell you about the if we use the metal, how to draw the most band diagram. Looks like this. As you as you know, I already mentioned this is the flat band because the Fermi level and the balance band is constantly, and you can notice the, the between the balance level and Fermi level is closer. So this is the p-type semiconductor, use the p-type semiconductor, and this is maybe n-type semiconductor. So in the matter, there is no conduction band and valence band, so we can draw like this one line, and you can you can see about this the Fermi level metal. So we already know about this Fermi metal like this. So in here, in this metal MOS diagram, we always have to maintain this offset, and this, and this. If we bias, if we injure the bias, it looks like maybe like this, and this is also same, maybe similarly. So we have to, okay, so now I'm gonna tell you about the how to draw the MOS band diagram simply, and the structure of the MOS, and maybe perhaps I will talk you about the important thing or the lot of contents about the MOS cap next week. So now I will finish this video. Thank you for watching this video, and I actually didn't understand about the MOS, so I will studying about the MOS cap, and next day I will tell you about the lots of thing about the lots of about MOS. Thank you.